Okay, so today what I'd like to do, I'd like to actually start talking about supersymmetry, and I'm sure a lot of you are familiar with this, with some of the things I'm going to say. So at the beginning, I'm going to talk from slides. I'll go to the board occasionally, but it's a little hard to see both. And then I'll switch over and talk on the board. But I just want to review a little bit some of the basics of n equals 1 supersymmetry. And so I'm going to do that. And we don't really have time to write lots of formulas, so I just want to remind you of things that most of you have surely at least seen, and I'm sure many of you are very familiar with. Okay, so yesterday we mentioned the basic supersymmetry algebra. Okay, that, let's see if I remember where all the devices are here. Okay, so in global supersymmetry in particular, we have some supersymmetry charges. And they obey anti-commutation relations, which give rise, on the right-hand side, one has the Lorentz generators, p mu. Okay. We remarked on this fact about the vacuum energy last time. So this is actually one quite remarkable feature of this algebra. Since we've heard a beautiful lecture about gravity, it's actually interesting to say something about this algebra in the presence of gravity, and also relates to some of the comments I made yesterday. So in gravity, as you know, this global translation generator p mu is not defined except in geometries which are asymptotically flat. And you perhaps not be surprised to learn that, in fact, the same is true of these q's. Okay, so in an asymptotically flat space, the q's will exist. They'll obey this. They'll also obey this algebra with p mu, where p mu is this famous ADN energy momentum. Okay? And one has actually this same relation then, even in gravity, for asymptotically flat spaces. And I mentioned yesterday that supersymmetry is something that can account for stability of a vacuum. And if you think about what this relation says, or think about what's relevant to tunneling in quantum field theory, well, I'm not going to give you a lecture on tunneling in quantum field theory, but if I want to imagine, in general, some sort of tunneling like this, okay, the way I tunnel is I take advantage of the fact that I have this negative energy over here, this negative energy density. And so if I can create a configuration of large enough energy density, a large enough size, okay, it will have large energy. So if this is some large r, it has some large negative energy. It has some surface tension. But as long as the bubble is big enough, the volume energy will win over the surface tension, and I will tunnel down here into the bottom. But in gravity, you see this can't happen, okay, because you can't make a negative energy configuration. Okay? So in supersymmetric theory, so supersymmetric states, okay, are stable. And it's something I think kind of remarkable. And while it's not in the usual list of things that people talk about when they advertise the virtues of supersymmetry, okay, I think it's something to be kept in mind, something quite interesting. And this is something that was actually first pointed out to me, at least, by Tom Banks and Ed Witten years ago. Okay, so I want to just talk a little bit about how we formulate supersymmetric theories. Okay, and so it's convenient to introduce an enlargement of space-time known as superspace, okay, to describe supersymmetric systems. And one doesn't have to, you can decide or not whether you want to attach some real significance, some actual geometric interpretation to this space. But one way we can think of this is just to view it as a way of realizing the supersymmetry algebra. Okay, so we want to write down something on which some functions of these variables, so we'll have some coordinates x mu and theta bar, these anti-commuting Grassmannian coordinates. Okay, 4 of these, theta alpha and theta bar alpha dot. We're going to write down functions phi of these variables x mu, theta, and theta bar. Those we'll call superfields. And the q's and q bars, these symmetry generators, will represent as differential operators on this space of functions. Okay, so they're going to actually be quite simple. So q alpha is dd theta alpha minus I sigma mu alpha alpha dot theta bar alpha dot partial mu. Okay, and I'm here using a 2-component notation for spinor variables. So the alphas are spinor indices, q alphas are spinors, or 2-component spinors. Similarly, q bar alpha dot is dd theta bar alpha dot minus I theta alpha sigma mu alpha beta dot theta epsilon beta dot alpha dot d mu. Epsilon beta dot alpha dot is the antisymmetric 2-index symbol. And if you've not done this, it's a valuable exercise just to check, for example, that these really are conjugates of each other and that they obey this commutation relation. Okay, that the commutator is p mu, which of course in this context p mu just means I d mu. Okay, and you see you're going to get I d mu when you take these anti-commutators. Okay, because of the d mu here, okay, and the fact that the d theta will act on the theta here, or the d theta bar on the theta bar here. Okay, so this is a very simple realization of this algebra, which is otherwise rather weird. Okay, so we're imagining we have some fields phi, which are functions of these x mu theta and theta bar. And so under a supersymmetry transformation, this means that the change in phi delta phi is epsilon q plus epsilon bar q bar. I'm sorry, this should be acting on phi. It's also, I should actually pause and say that these notes, including the typos, are available online. So any of you who are dying to read these, when you get home, they're there. And I didn't write down the URL, and I don't remember the URL, but if you just Google Michael Dine, you will come up with at first I thought, oh, you Google Dine Jerusalem, but of course that first gives you 25,000 restaurant listings, and then finally you would find me somewhere way down there. But if you Google Michael Dine, you'll find my webpage, and you'll find a link there to these, and it will be obvious to these lectures. Okay. So so it's also convenient to introduce a set of covariant derivatives. And these probably have some deep significance, which I don't really know, but some deep geometric significance. But they're very useful because you see they look a lot like the Q's, which we just defined. They're just some sign differences. But what's nice about them is they anti-commute with the Q's themselves. And so they allow us, they're very useful in constructing invariant objects. Okay, objects which are invariant under these kinds of transformations. And so they're quite valuable and important in the construction of supersymmetric field theories. Okay, so in fact, we have sort of this general idea of a superfield. I should say, by the way, that because the thetas anti-commute, okay, and again, this is something familiar, I'm sure, to most of you, but because the thetas are anti-commute, okay, the product of any two thetas, the theta 1 squared or theta 1 bar squared, okay, is 0. So all these functions are polynomial. These phis, these superfields, are all polynomials in the thetas. And you might say, well, that's great, because then we don't have, there are only a few terms, some finite number of terms, okay? But, and so we should be able to work rather easily with them. But it's even better than that. We have two interesting, what will be for us, two interesting irreducible representations of the supersymmetry algebra. One known as chiral fields, okay, which satisfy this constraint d bar alpha dot phi equals 0. Okay, and another, which known as vector superfields, which satisfy a reality condition v equals v dagger. Now, if you think about this transformation law of the fields, okay, each of these conditions is invariant under supersymmetry. And I know it's a little hard to see in the back with the lights down, but I'll write it down anyway. So if we look at d bar alpha dot phi equals 0, okay, then d bar alpha dot q beta times phi is equal to minus q beta d bar alpha dot phi equals 0. So this condition is preserved under supersymmetry transformations. Okay? And the v equals v dagger condition is also preserved. So these are two irreducible representations. They allow us to write something, a representation of the supersymmetry algebra in terms of a smaller number of fields than we might otherwise guess. And so I've written the case of the chiral field here. So phi is a scalar field. Okay? And in my notation, I will freely, when I actually write things, I'll often use the same notation, the same letter for the scalar field as for the whole superfield. For the fermion, I'll usually put psi with a subscript. Okay, and the fermion comes here with a theta. So the product is a spinor times a spinor is a scalar. And there's some root 2, which is just for convenience and probably not the same as anybody else's convention. And then there's a field F, something involving theta squared, which is which we'll see as an auxiliary field. It will appear, it won't, when we write a Lagrangian for this theory, the field F will not appear with derivatives. Okay, so we can just solve for it by its equations of motion. It's interesting because it is itself supersymmetric. Under a supersymmetry transformation, it's invariant. Okay. I should say it's also interesting because it is the order, we'll see in a moment, it's the an order parameter for supersymmetry breaking. What question? Sorry.
Yeah, theta squared, is that theta bar?
Or no, it's theta alpha. Can people see it all? It's theta alpha. So remember theta. So unfortunately, I don't have time to introduce. Well, maybe fortunately, I don't have time to introduce a lot of notation. Thank you. To introduce a lot of notation. But theta. So theta alpha. There's some theta 1, theta 2. It's some two-component spinner. Okay. And this object at theta alpha means epsilon alpha beta. This two-index antisymmetric tensor. Theta alpha, theta beta, right? Or it's theta 1, theta 2, minus theta 2, theta 1, which is just twice theta 1, theta 2, since the theta is anti-commute. Okay, so it's the thetas. And the theta bars are the conjugates of the theta. They're essentially the complex conjugates of the theta, just like for two-component spinners. For example, if I represent an electron in terms of a two-component spinner, I have an E and an E bar. Okay, one with one charge, one with the opposite charge. And so the E, for example, I can think of as creating an electron of one helicity and annihilating a positron of the opposite helicity. Okay, and similarly, the E bar sort of has the reverse role. It creates the other electron of the other helicity. And so I have E and E star, and E bar and E bar star. Okay, so this switches creation and annihilation operators. Right, so this complex conjugation, in that case, switches the role of A's and A daggers, or B's and B daggers. Okay, this is in the back of these notes. Actually, there is a little review of two-component spinners for those who, this is probably more valuable than almost anything except Eric's lectures at the school if you learn what two-component spinners are. Okay, if that's not familiar. Okay, so so this is our basic field. Let's go on. So I've been I've actually used a little shorthand here, so now we could put the lights down again. Yeah, thank you. So actually this phi is really, I was a little sloppy. The phi is actually a function of a variable y mu. This y mu has the virtue that d bar annihilates it. So d bar, this object d bar annihilates it. Again, a little exercise you can do. Okay. And then you can ask now, what are the supersymmetry transformations of these various fields? How do the component fields, this is sort of really what I at least personally care about, how do the component fields transform under the supersymmetry transformations? And so, for example, the change in the scalar field involves the fermionic component. So C here is the parameter of the supersymmetry transformation. So I'm doing a transformation by CQ. So Q, remember, is a spinor variable. It's an anti-commuting variable. And this C is another variable like these thetas. It's a parameter, but it's an anti-commuting number. Okay? So that makes this thing a scalar. It's a little, so this thing on the right is a scalar, but it's not, it's kind of a boson and it isn't. Right? Because so again, it's something sort of interesting to think about here. It's a sort of like, where Bose statistics is. Okay? The change in psi is actually in some ways more interesting. It involves square root of 2cf, okay, and some stuff involving derivatives of A. Okay, and the change in F involves derivatives of the fermion. Okay, so we want to think, so if I could pause here, okay, and I said something yesterday about supersymmetry breaking. So I said yesterday that the order parameter for supersymmetry breaking is the vacuum energy. Okay, and now we can think about this in a slightly more sharp way already. Okay, so in particular, if F is non-zero, if in the vacuum F is non-zero, and we assume the vacuum preserves Lorentz invariance, so I'm only interested in constant fields. So if F is non-zero, then psi changes. And this is a signal that the symmetry is broken. Okay, so this is exactly what happens for a Goldstone particle, for example. So in the Goldstone phenomenon, you have the field change. The field has a net. is not invariant. If you do a transformation, okay, it changes because you have some vacuum expectation value for a field. Okay, so this is a signal of the symmetry breaking. And again, it's sort of hard to see in the dark. But again, that's the idea here is that delta psi is, am I going to write this right? I'm sorry, QF is delta psi. Okay, and if delta psi has a non-zero transformation law, this corresponds to the fact that this thing, I'm still not writing this right. No, I'm sorry, I'm writing this wrong. Q psi is F. Sorry, I'll get it right. Q psi is F. Okay, and if this has F has an expectation value, so does this. This means Q doesn't annihilate the vacuum. So this is kind of standard Goldstone phenomenon. And in fact, what happens in this case, and I won't have time really to talk about it very much, is that the psi in that case is the Goldstino, just as in ordinary Goldstone phenomenon you would discover the pion. Okay? So this is sort of an interesting set of equations to stare at. Okay? We won't need it that much, but it's sort of useful to be aware of. Okay? Now the vector fields can also be written in superspace. And I've written an expression here where I have a lot of stuff in here. Okay? There's a chiral field chi. So chi, remember, has components which are no thetas, 1 theta, 2 thetas, a theta and a theta bar, okay, and so on. Okay, so there are a bunch of components here. And then I have some additional pieces, except again with, oh no, this is all right. I have a piece with, no, I'm sorry. Something bad. Yeah, this is theta. This should be theta sigma mu theta bar. So it should be a theta theta bar. This is a mu, the gauge. This will be the gauge field. Okay, I have theta squared theta bar lambda bar and theta bar squared theta lambda. So this lambda is a fermion. These are terms with 3 thetas, and then I have a term with 4 thetas with a d. Okay, so a mu is a vector field. Lambda is a spinor field, a 2-component spinor. D is another scalar field. It's an auxiliary field like this field F. Okay, and this chi, turns out, we're going to be able to gauge away. So this chi is a bit of a, well, it's not really a fake, any more so than any other gauge degree of freedom is a fake. But in terms of isolating physical degrees of freedom, we have here the gauge field and a gaugino. And if we think about the physical degrees of freedom of that, okay, there are 2 degrees of freedom in the 2-component fermion, and there are 2 degrees of freedom in the gauge field. So we have this equal number of bosonic and fermionic degrees of freedom, which actually should have stressed we have here also. Okay, so here we have a complex scalar, so it's 2-component. It's 2 degrees of freedom here, and a 2-component spinor, which are again are 2 degrees of freedom. So we have equal numbers of Bose and Fermi degrees of freedom. Okay, so in order, now we know because we have this gauge field here, we expect that there has to be some sort of notion, or we have a vector field, I should say. We expect that we should have some notion of gauge invariance, and we do. Okay, so we have some generalized notion of gauge invariance. And the gauge invariance involves a chiral field lambda, and we can in general make a transformation of V. V goes to V minus lambda dagger. And what that does, let me back up here for a moment. Oops. So what that does is by just choosing lambda suitably, we can get rid of this chi. So that'll allow us to gauge away this chi. Okay, and so V goes to V minus lambda dagger, and phi goes as e to the charge of the field phi. So phi I goes to e to the qi, lambda phi I. So we'll be able to form gauge invariant combinations like this shown here, phi I dagger, e to the qi v phi I. You can just check this. You can check by I. Okay, is gauge invariant. Okay, so this is a gauge invariant combination. Okay, in the non-abelian case, there's a more complicated transformation law. Okay, the gauge field can be thought of as a vector, as a matrix-valued field. Okay, lambda is also a matrix-valued field. Okay, but it incorporates the same idea, and it's a bit of algebra just to sort of figure out what it is. Okay. All right. So as I say here, I'm just repeating myself here. We can gauge away this chi. Okay. At this point, I still have this lambda bar. Okay. This should be theta sigma mu theta bar. Okay. So this is theta and the theta bar, a mu, theta squared theta bar, lambda bar. Okay. And lambda. So these lambda and lambda bar are complex conjugates of one another, and I have theta squared, theta bar squared d. Okay, so this is a little bit like choosing the Coulomb gauge. Go ahead, Christian.
Yeah, sorry. So why was the previous slide an example of a Goldstone phenomenon? Sorry, the one before. Here, yeah.
Oh, here only if f has a vev. So if f has a vev, okay, then again, let's see if I can. See, I don't know if we can get the lights back. So if you think about the ordinary Goldstone phenomenon, so if I think about the ordinary Goldstone phenomenon, where I have, my Mexican hat potential, and I have some field phi, which I can think of as being sigma e to the I pi. In fact, let me think of it as sigma plus v e to the I pi, okay? Then under a symmetry transformation, under the symmetry transformation, okay, delta phi, right, what is delta phi? Delta phi is some alpha, is some I alpha times phi, where phi is my transformation parameter, okay? And if I have an expectation value for phi, okay, I have some expression like this. The way this works is that this pi, right, this Goldstone boson, okay, delta pi is I alpha times the expectation value of phi, where the expectation value of phi is, say, something you would call the pion decay constant. And here I have an analogous situation. Okay, if f has an expectation value, okay, delta psi, okay, is delta psi like here is equal to some constant, some parameter, some transformation parameter c times f. And you see that the transformation parameter for the pion, okay, for the U1 is very much like the pion field. And similarly here. Okay? So I don't want to make a big point of this. I just wanted to say there is a Goldstone phenomenon, and you see it by analogy to this phenomenon that you're familiar with already for pions or for Goldstone bosons more generally. Okay. So all right. So I just wanted to, again, to say that so we have this vector potential, or we have this vector field, which superfield, which plays the role of vector potential, and we can define also a field strength. Okay, an object which is gauge invariant using these covariant derivatives, d bar squared d alpha v. For the U1, it's very easy to check that this is gauge invariant. You use the fact that d bar alpha of lambda, this quantity lambda, is 0, and the fact that the d bars and d's have a simple anti-commutation relation. Okay, and in terms of component fields, this W alpha is simple. W alpha involves this gaugino field, this auxiliary field, the gauge field, and then some stuff involving the derivative of the gaugino. Okay. So I think I'm not going to write for you the non-abelian case. I'll let you just believe it, and just say then a few words about how we construct supersymmetric actions. So for these variables theta, we have very simple integration rules, which you've seen which you've encountered when you've encountered path integration for fermions. Okay, so you have these variables that just basically integral d theta of 1 theta, integral d theta 1 of theta 1 is 1, integral d theta 1 of 1 is 0. That's the whole integration table. Okay, in terms of these objects theta squared, which we wrote before, these theta alpha, d2 theta theta squared is d2 theta theta bar squared is 1, d4 theta theta squared theta bar squared is 1, and all the others vanish. So for example, an integral d4 theta d4x f is invariant under supersymmetry transformations because the supersymmetry generators involve either derivatives with respect to theta or derivatives with respect to x. So when we integrate, so it's much like translations. Okay, we have invariance of the Lagrangian once we integrate. Okay, so in this case, any Lagrangian of this form is invariant. Integrals over half the superspace of chiral fields are also invariant, and again, because Sorry about this. I'm used to rooms where I can control the lights. So just to say why this is true, so if I integral due to theta of some chiral field phi, okay, phi of x and theta, this is supersymmetric. Why? It's supersymmetric because if I act with the q alphas, okay, q alpha, remember, involve d alpha. So I also want to put a d for x. Involve d by alpha and d mu. Okay, so this object is automatically invariant if I integrate over the thetas or I integrate over d4x. Okay, so these types of supersymmetry transformations, things which some parameter c alpha, q alpha are automatically invariant. What about c alpha dot, q bar alpha dot? So here it's slightly less obvious. It's less obvious because we don't integrate here over theta bar. And q bar involves d theta bar. But here we can take advantage of the fact that the supersymmetry generator can be written. Remember, they all look very similar, the d bars and the q bars and so on. The q bar can be written as d bar plus something involving a derivative. Okay, so the d bar here annihilates the chiral field. Okay, and the other derivative we can again integrate and get 0. Okay, so we have, and this fact that we can integrate over half the superspace is very critical in our understanding of supersymmetric field theories. So for example, all the marvels, which we'll talk about in a moment, of NaNormalization and so on, are almost all consequences of this fact. Okay, of the fact that the integral d2 theta of any chiral field is invariant. Okay, so with that, with only that, okay, we can write down an action, a supersymmetric action for gauge fields and chiral fields in the following form. We can write something which involves a d4 theta, phi I dagger, e to the v phi I. This we said was gauge invariant. Okay, and it's supersymmetric because we integrate d4 theta. And here I'm summing over whatever fields I have. And then I can write a term which involves a d2 theta of this w alpha squared. This field strength was a chiral field. Okay, so we'll d2 theta alpha, w alpha squared. We'll have to add the complex conjugate. And then we have this function, this famous function called the superpotential, w integrated d2 theta, which is a function of chiral fields. So any function of chiral fields is itself a chiral field. Okay, so d bar of phi I is 0, then d bar of phi squared, and so on are 0. So this integral is, this w is a chiral field. Thought of as an ordinary function, thinking of these phi's as ordinary functions, okay, what this statement is that w is an analytic, or more precisely, a holomorphic function of these phi's. Okay, so this superpotential is rather critical. I think it will appear in some of the other lectures in this school.
Sorry, the v in the exponent, is that the vector superfield?
That's the vector superfield.
But it has components.
They all have components. Right, so this is all written in terms of the superfields, okay, and what will give us, the integral d4 theta will give us an expression which we can write in terms of the component fields. Okay, so I'll do that in just a moment here, actually.
I mean the index on the v.
Oh, the v, yeah, I'm sorry, for a non-abelian theory, the index is, yes. Okay, so what I have in mind here is that phi I, so I've written in a somewhat abstract way. So as I said, I was thinking of v. So in general, if I have a non-abelian theory, I'll think of v as a matrix-valued field. So for example, for SUN, it might be a sum VA of some Hermitian generators. Right. And in that case, and then the phi's will be sit in some representation of whatever the group is. So the I here, so in my mind, the I here represented, I might have some set of fields. And I will do an example in a couple minutes on the board. I might have some set of fields transforming in a particular representation. The I would sum over all the different fields in different representations. Okay? And I've sort of suppressed the fact that I might also have a U1, in which case I would, instead of writing a matrix-valued field, I'd write some charges here times the V's. Okay? So this is kind of shorthand for a lot of stuff. So where are the derivatives? The derivatives are in the superfields.
Yeah,
Okay.
see, the first term is 1.
The first term is 1, and doesn't. Yes. So let me go ahead. We're going to write. So here's the action. Let me tell you where the various terms come from. Okay. So I say, unfortunately, I don't have. It takes 4 lectures or something to, the reason I'm kind of doing this hasty thing is to sort of put everyone at this more or less the same level. And as I said, this is all online, and if you've not seen this for any number of reasons, it's good to practice with it a little bit. So let me describe what this action describes. So what would we expect? Okay. So we kind of know a large part of the answer. Okay, so if we look here, this chiral field, remember, has a fermion and a complex scalar. Okay, and the W alpha has gauge fields, okay, gauge bosons and gauginos. So at the very least, what do we expect? We expect to see kinetic terms, gauge invariant kinetic terms for the scalars, gauge invariant kinetic terms for the matter fields, the fields in these chiral representations, the gauge invariant kinetic terms for the gauge fields, and gauge invariant kinetic terms for these gauginos. These gauginos, I should say, because they are also matrix valued fields, okay, are in for a non-abelian group will be in the adjoint representation of the group. For U1, they're neutral. They're just neutral fields, so we have gauge invariant kinetic terms for all of these fields. I've normalized things, so I have a 1 over g squared in front of the kinetic terms for the gauge fields and the gauginos. And then there's going to be other stuff. So, but let's first ask, where did some of these terms come from, just at least schematically? So again, I need the light. Thank you. So let's think about some of these terms. So let me do an example. Let's just think of one example. So let's suppose I have something like phi dagger phi. I won't worry about the e to the v for a minute. So for the phi dagger phi, remember phi dagger, or phi rather, has terms. It has a term that was like a, the scalar. It has a term square root of 2 theta psi. And then it had stuff like, well, it had a term theta squared f. And it had more pieces, right? It had more pieces. It had things like theta sigma mu theta bar d mu a. Okay, so let's look at this one. Okay, so I have a term in phi which involves a theta and a theta bar and a derivative. I have a term in phi dagger which will involve a star and again a theta and a theta bar. Okay, so in the product I have 2 thetas, 2 theta bars, 2 derivatives, okay, and 2 fields. Okay, and that's going to give the d mu a squared. So you have to do a little computation to make sure that you've normalized things the way you want and the 2's appear in the right place. But it's going to give you something that involves d mu a squared. Okay. Similarly, for the fermions, okay, I have a term also here. I have a term that involves theta psi, theta bar sigma mu theta d mu psi. Okay. So I have a term like this, and then the phi dagger term, which involving theta bar psi dagger, will give me the kinetic term for the fermions, and so on. Okay. And I'll get a term which involves f dagger f, just with no derivatives, from the theta squared here and the theta bar squared here. Okay? So all the terms are there. It's somewhat tedious algebra, which I kind of did once in my life and convinced myself that I'd done my duty and I don't do it again. But to see that with the square root of 2 here and so on, that I get a nice normalization of the fields. There's nothing that deep in this. I could have put square root of 17 here, and I just would have had some weird normalization for the kinetic term for the fermions. Okay? So that okay? Okay. So, so now that you know how to do these integrals in this quick lesson, we have more couplings. Okay? We have Yukawa couplings of the gauginos and the matter and scalar matter fields, the psi's in the chiral fields and the phi's in the chiral fields. Okay? So they come just like for gauge fields, they come with some TA, or if we had a U1, they would just come with the charges of the fields. Okay? And we have a complex conjugate here. And the thing that's perhaps worth keeping track of is we have psi, phi star, lambda. So just like we would have A star, lambda, we have psi, phi star, lambda. Okay? And then we have a term which arises from the involving the fermions in the superpotential d2w, d phi I, d phi j, psi I, psi j. Okay? And we have a potential for the various scalar fields, which can be written in terms of the auxiliary fields, these FIs. These FIs you can show are dw, d phi I. So we get Fi is dw, d phi I squared. Okay? This comes from the fact that, well, I don't want to do the lights again yet. I'll do it for you in a moment. These D's here are GA, phi I star, TA, IJ, phi j. Okay? So I think this is a good point to move. So this was a very, this was a hasty description of the first half of the book, the text by Wesson Bagger, for example. And at this point, it would be good to, if we could have the lights, and then the poor session chair can sit down. We'll go to the blackboard. And Eliezer, you said we were quitting at 2?
1, 2.
It's OK. Yeah. So, I need to undo this light here. Sorry. It's this button. Question is, do I remember? Am I right? No, wrong button. There's so many things here. Here we go. OK. So all that, as I say, for some of you that was pretty boring, and for some of you that was too fast. But let's illustrate with some simple examples. OK? So let me take a very simple model first with a single chiral field. Phi. Okay? And let's take that field, so no gauge fields, no gauge symmetry or anything like that. And let's just take W to be a half m phi squared. Okay? And now I'm just going to recall some of the formulas which I wrote up pretty fast over there. So let's first of all ask what the potential is. So I said for the potential we have to calculate this object F. And F is I'm going to just take F to be dw, d phi. I should be a little more careful. Actually, I should put phi star, I guess. So I'll take F to be dw, d phi star. I actually could put a minus sign in there, but I won't bother. Okay? And to remind you where this came from, in terms of these integrations we were doing, we had some integral d2 theta, w phi. Okay, and remember phi is, for example, involves this scalar, which I'm now going to call phi again to be maximally confusing, plus theta squared f. Okay, so if you like, let me put capital phi here so we distinguish them in some way. But eventually, I'll just sort of jettison that. Okay, so to get a non-zero result here, I need 2 thetas. Okay, so how do I get 2 thetas? Well, I expand phi out to get this theta squared f. So this is, in fact, integral d2 theta dw d phi, dw d phi, now dw d phi, where I'm differentiating with respect to this object, and theta squared f, okay, which is dw d phi times f. Okay, remember the kinetic term for f, the term that came from the d4 theta was f dagger f. So my Lagrangian involves f dagger f plus dw d phi f plus dw d phi star, dw d star, d phi star, f star. Okay, so if I differentiate with respect to f, if I just look at the Euler-Lagrange equations for f, delta L, delta f, or delta L, delta f star, I get this f is, I actually get f, let me put the minus. I get f is minus dw d phi star. Okay? And in this case, it's just if I keep that minus sign, I'll make mistakes. But so I'm going to drop it. Okay, so what is it in this case? So this is m phi. Okay, f star is m phi star. And the potential, we said, v is f star f. Right, so this is m squared. And I'll put an absolute value of m, because at this point, m doesn't even have to be real. M is just a complex parameter. M squared f squared. M squared phi squared. Okay, so we have a massive scalar, a scalar of mass m. Okay, and now similarly we can look at the fermionic part of the Lagrangian. The fermionic part of the Lagrangian we wrote up before, it involved d2w and a half, d2w, d phi partial phi squared, okay, times psi, okay? And in our case, this is a half m psi. This is the Lagrangian for a two-component spinor, or a Majorana spinor, if you like, in this case, of mass m. So we have a fermion and a boson of mass m. Okay, of mass m, or I should say mass squared. Let me be a little more careful. Mass squared m squared. Okay, so we have two fermions and two bosons degenerate in mass, okay, so this is sort of one indication that this theory is supersymmetric. Okay, now we can complicate this theory a little bit by adding. In fact, let me just do it here. We can turn this into an interacting theory by adding a term phi cubed. This theory is known as the West-Cimino model. And it's kind of, well, okay, again, it describes two fields of, it describes a complex scalar of mass squared m squared and a complex fermion, a Weyl fermion with same mass. Okay, but it now also describes interactions. So in particular, if I take this formula I wrote for the fermions, we have now this d2w d phi squared psi. So in addition to the mass term and a half, we have also a term lambda phi psi. So we have a Yukawa coupling of the scalar to the fermions. Okay? And similarly, we have in the potential, this f star is now m phi plus lambda phi squared. So f squared, this is f. F squared is m phi plus lambda phi squared. Okay? And so the Lagrangian includes a cubic and a quartic term, okay, for the potential for the scalar fields. Okay, and in fact, at this point, we could take a moment and ask, well, we started out trying to motivating this by wanting to see some cancellation between fermions and bosons, right? We talked about naturalness, and we talked about this notion that in some limit, the scalar should be massless. So let me put m equals 0. Okay, and let's compute the one-loop correction to the mass of the scalar. Okay, so for m equals 0 in perturbation theory, first of all, in perturbation theory, because of the sort of chiral symmetry I talked about yesterday for the electron, the fermion mass is 0. Okay, so we can ask now let's ask about the mass of the boson. The symmetry better ensure that the mass of the boson is 0, and we can just see that at the level of Feynman diagrams. I don't know if Tzvi's still here, but. Anyway, so we can write, so in this case we have we have two diagrams. So okay, we have a diagram with, we have this quartic coupling now, m's not here anymore. So we have a quartic coupling, this lambda squared phi squared, okay? And we have a loop involving the Yukawa coupling of the fermion, okay? And so the result here is lambda squared, sine integral, okay? And we have a term that's 1 over k squared from here. But from here, we get the same expression. Okay, we also get a minus 1 over k squared. Actually, I should be careful. There's actually a 2 when you do the combinatorics correctly. So there's a 2 over k squared here. The minus sign is the usual minus sign for Fermi statistics, for a fermion loop. Okay? And so we get that m squared is 0. Okay. Now at this point, actually, it's worth saying that if suppose I now tried to break the supersymmetry a little bit, just by hand. So how might I do that? I have my Lagrangian. Okay, so my Lagrangian is the kinetic terms for all the fields. And then there's this lambda phi psi psi. And then there is lambda squared phi to the fourth, or minus lambda squared phi to the fourth. And now let's just add a little term, I'll call it m soft squared for the scalar phi squared. So let me just add it by hand. Okay? And at this point, I've broken the supersymmetry. Okay? Much like we broke in QED, we broke the chiral symmetry of the electron. Okay? And in that case, okay, this computation is modified. How? I have this becomes k squared plus m soft squared. Okay? Notice, by the way, each of these terms is separately quadratically divergent. It's the divergence we talked about yesterday. Okay? And now, this expression, well, it's not quite finite, but it's almost finite. It's lambda squared minus m soft squared. Okay, and then I have an integral d4k, should put my 2, over 2 pi to the fourth, and now k to the fourth. Okay, so what I've done, to do that expansion, I've looked at the high energy behavior of the integral. I should really cut it off at the low end then by m soft. Okay, and so this is minus twice lambda squared m soft squared log of some ultraviolet cutoff, and there's some 16 pi squared, and log of some ultraviolet cutoff divided by this soft mass. Okay? This computation is very simple, and it's a very sort of basic one in understanding the issues that are going to arise when we think about making supersymmetric models, when we think about the current status of supersymmetry in the hierarchy problem and questions of tuning. For us, what's going to happen, this lambda will be the top quark Yukawa coupling, okay, and m soft, for example, might be the mass of the stopped quark. Okay, so this will be this very simple computation will be very basic to our understanding of what's going on in supersymmetric theories. So let me describe a couple other models, and then I'm going to come back to this one. Well, actually, let's leave this one up here for a moment. Okay. So,
in this model, is there another in higher order perturbation theory corrections to the mass?
No. No, and to prove that, this is a very cumbersome way of, well, I'm sorry, with the soft breaking terms, yes. Without the soft breaking terms, no. So if I put m soft to 0, then the result's exact. To prove that, you need to, this kind of method becomes awkward. You don't really want to work in terms of the component fields, but you want to work in terms of the superfields more directly, and you can formulate the Feynman graph expansion in terms of objects in superspace, for example. And there you can prove it quite trivially. Okay? I'm actually though going to prove something more general about this theory and the corrections to this theory. So what I'd like to argue is I'm going to prove now that lambda is not renormalized. Okay, and I'll put a little star here because there's a subtlety that I have to describe with that. But I want to, so this is an example of the so-called non-renormalization theorems. Okay, so supersymmetry, one of the things that gives supersymmetry its interest in all its forms, the forms that you're hearing from Nikita, the forms that I'm going to use, the forms that occur otherwise. A lot of the interest in supersymmetry comes from these, especially supersymmetry as a kind of interesting class of field theories comes from this fact. These are field theories. The fact that we can control these field theories so well comes here. And so here this provides us just a very simple example. Okay, so let's think a moment about the symmetries of this theory. So first to start this, I have to start by describing the symmetries. And at first sight, you might say, well, there probably aren't that, well, maybe there's a Z3 symmetry or something, but what else? But this model actually has another symmetry. So in particular, let me first do lambda equals 0. Okay. So for lambda equals 0, W equals ½ m phi squared. Okay. And now you might say, well, OK, I can't, OK, if I just rotate phi by a phase, W changes, so it's not a symmetry. But things are more subtle than that. There's a class of symmetries, which are going to be very important to us, called R symmetries. And I don't remember why they're called that. I think it's a term due to Fayet, and it had to do with some kind of models he was building in the mid to late 70s. But these symmetries have the following feature. Okay, they these are symmetries which commute with the Hamiltonian, but not with supersymmetry. Okay, and in particular, the Q alphas will rotate by a phase. Okay, and so the way you can understand this, remember that the Q alphas. What was Q alpha? Q alpha was something involving d theta alpha plus some I and theta sigma mu, theta bar sigma mu d mu. Okay. So so in the superspace language I used, what this will correspond to is that the fields phi I rotate by some phase, the superfields. So I'll call it either I alpha phi I. Okay, but the thetas also rotate by a phase. So if I do that, then the Q's rotate. Actually, the way I've written it, the Q will rotate with an e to the minus I alpha. That's because d theta alpha is invariant. Theta beta is invariant. It's just a number. Okay. So and this is a general feature of these anti-commuting variables. D theta is sort of like 1 over theta. Okay, and so the d theta will always transform like theta star or 1 over theta. Okay, and so now what does that mean for W? Okay, for W, this means that W transforms. If integral d through theta W is to be invariant, this means W transforms with charge 2. All right, so this theory has a symmetry. Okay, this symmetry has a symmetry where phi has charge 1. So phi has R charge 1. Okay, that actually means that the scalar component of phi has R charge 1. Its fermionic component has R charge 0. It has 1 less unit of R charge. And the F component has R charge minus 1. Okay, so if I think about the component Lagrangian that I wrote before, okay, I have things in that component Lagrangian that look like psi, psi, I'm going to be on, I'm sorry, which look like psi, psi. Okay, so that's invariant. I have things that look like F phi, which is also invariant. Okay. So these symmetries, so the things that among the things that allow us a great deal of power in these theories are these R symmetries and are these R symmetries and this holomorphy of W. Okay, we've already heard mention, for example, of n equals 4 supersymmetry a lot. In the n equals 4 theory, okay, the R symmetry is richer. The R symmetry is actually an SU4, which rotates the supercharges, and we'll actually mention that a little bit later. Okay, so these symmetries are rather rich. Okay, so let's think about now this theory with m equals 0. Okay, so now let's think what happens when we add this lambda over 3 phi cubed. Okay, so now when this breaks, it's the continuous R symmetry. But we can pretend, and maybe sometimes it's not even pretending, but we can pretend that lambda is the expectation value of some chiral field. Okay, such a thing is usually called a spurion. Okay, and if we do that, okay, then we have to, in order that the Lagrangian be invariant, okay, so now I go back to my Lagrangian. So my Lagrangian, for my Lagrangian to be invariant, lambda has to have R charge minus 1. Okay? So now let's ask what kinds of terms, what kind of corrections, if we imagine computing some kind of effective action, what kind of corrections can appear in that effective action? So the changes which could appear in W, changes to W, so W has to have R charge 2. So we can have what? We can have, for example, let's do an example. We can have phi to the 4th, phi 4th, okay? And then we need lambda squared. Okay, we could have lambda cubed phi 5th. I have some coefficient here. Okay, and so on. So what are these terms? Okay, so where would I get this phi 4th? Well, I would get phi 4th from just the tree diagram, phi, phi, phi. This is my coupling of 3 phi's. And I can have my mass term here, and I have phi, phi. So I can draw things like that. I can draw tree diagrams which give phi 4th. I can draw a tree diagram for phi 5th. Okay, but I'm not allowed to write any corrections. Okay? Remember, the important thing is that W is holomorphic in lambda. This is what Seiberg calls the power of holomorphy. Okay, so I can't put lambda star anywhere. So this exhausts the lambda dependence of W. Okay? And so what we learn is that there are no quantum corrections to W. There are no loop corrections to the superpotential. And you can check this at the level of Feynman diagrams. It's sufficiently outrageous that you can check it. And in fact, it was known long before this argument was arrived at that, in fact, all the diagrams, all the corrections to lambda cancel. So this is a simple example of these non-renormalization theorems. Okay? Now, okay, is that okay? Why is it important? Why is that important, or why is it what doesn't get? Why is it true? It's true. It's true because, it's true because I can't write a phi cubed. First of all, I can't write the only phi cubed. This is delta W. So delta W can't have a phi cubed correction in it. So there's no correction to phi cubed, and everything at higher orders, okay, is fixed by this structure. Let's talk about non-abelian theories, and we'll make an even more outrageous statement, which I will then try and resolve probably tomorrow for you.
But you would generate some new terms in the algebra.
You'll generate new terms. So for example, you can generate derivative terms. Tree graphs will generate these terms I've written here. You can certainly generate derivative terms. You can have, for example, modifications of the kinetic terms. So we have phi dagger phi. And then this can be 1 plus some function of lambda. Because I'm allowed, right, these terms don't, because they involve integrals d4 theta, they don't have to be holomorphic in lambda. So at least from this argument I'm giving here, there's no restriction on those. So I have to go and compute those corrections. I don't have any, and I can't make any statement I can't make any statement reliably without doing, that depends on the structure of these corrections. This, I should say, by the way, is this structure here is called more generally is called the Kähler potential, this function of phi dagger phi that appears here, and a little figure and other things we talk about.
And those corrections to the Lagrangian controllable, or
I'm sorry, the contractions to the I just couldn't hear.
Controllable, or they?
Yes, sure. Sure, but they're corrections. Oh, well, the corrections to phi dagger phi will be ultraviolet divergent. There will be some wave function renormalization of the field. Beyond those, they'll be controllable. So the theories were normalizable in the traditional sense, and I can compute the higher order corrections to the higher order polynomial corrections, for example. In phi, I can compute. Okay, so all right, so let's talk a little bit about gauge theories. Okay, so let's illustrate. So this was a simple illustration of a theory involving chiral fields. So let's talk about gauge fields. And this partly just give us a chance to practice with those formulas which I just flashed up for you. So let's do something simple. Let's do a version, a sort of a generalization of massless QED. So I'll have, to do that, I'm going to have a chiral field with charge plus under some U1, and a chiral field with charge minus. And I'm going to put W equals 0. No superpotential for these. I could put something like phi plus, phi minus, which would be a mass term for these fields. But let me leave that out. And let's look then at what does the Lagrangian look like? In terms of the component fields, the Lagrangian, remember, has the kinetic terms. It has d mu phi plus squared plus d mu phi minus squared plus so on, the kinetic terms for everybody else, the kinetic term for the gaugino, the kinetic term for the gauge fields. Okay. But what I want to focus on is the potential for the chiral fields. So that, remember, was written in terms of this object d squared. And in fact, I called it 1 over g squared, the gauge coupling d squared. And then there were also Yukawa couplings, lambda phi plus, so with a g and a root 2, I guess. Lambda phi plus star psi plus minus lambda phi minus star psi minus. So the fermion, psi plus is the fermion in here, psi minus the fermion there, phi plus and phi minus the bosons in the corresponding fields. And then there's plus the complex conjugate. So this is the problematic blackboard. Okay? Okay, so, and now let's look a little bit at some of the features of this theory. So one of the features you notice, if you look, so let's first look at D, what D was. D was, in general, I wrote it for non-abelian theory as I wrote it as sum over the various fields phi I star Ta phi I, where Ta are the appropriate generators for the phi I. For our U1, this just means phi plus squared minus phi minus squared. Okay. And what's interesting about this theory is that if I look at this potential, the potential, okay, so you're used to talking about the Higgs field, and the Higgs field has a potential, and it's got a minimum somewhere, and you expand about the minimum. Here we have lots of minima, okay? And they're not just the minima controlled by the gauge symmetry. So basically, I can have phi plus equals phi minus. Let's see, I put the index upstairs. Obviously, I'm flipping upstairs and downstairs. I'll try and be. So I can phi plus equals phi minus equals v, some number. I could put a phase in here, a relative phase, but that relative phase is, well, we'll talk about that phase. Let me not worry about the phase for a moment. Let me just set them equal. Okay? And each of these, when you do quantum field theory, okay, each such choice has to be thought of as a distinct choice of vacuum for the theory. So we have a set of distinct vacua. And what you can see is that the masses, and they are physically distinct because the masses depend on, fields depend on V, right? So the masses of the gauge bosons, for example, will be something like g squared, there may be a 2, v squared. In fact, I think there is a 2. Okay? And the masses of the gauginos, okay, will also depend on this V. Right? Because for if I put just a number here, if I put this V here, this is a mass term. It's a Dirac mass term for the field, some linear combination of the field psi plus and psi minus. So there's a, so this is actually, so we have this is 3 bosonic degrees of freedom. Okay, there are 4 fermionic degrees of freedom. And again, I won't offer you a money-back guarantee for the 2. Okay, I'll let you do that as a homework exercise. Okay, but so there are 3 fermionic degrees of freedom. Okay, now there's one scalar we lost there somewhere. There's one so right. So these 3 degrees of freedom are the 2 transverse degrees of freedom of the gauge field and the Higgs field, and then there's the Higgs field, the thing that got eaten. Okay, so 3 there. Okay, the 4th is the other scalar. So one linear combination of scalars is eaten in the Higgs mechanism. 1 gets mass in d squared. Okay, when I expand this about its minimum, about this point, I get another boson of the same mass. So I get altogether 4 degenerate bosons, okay, and 4 degenerate fermions. Okay, and so the theory is supersymmetric. Okay, now this feature, okay, that the vacuum is not determined is both interesting and it's a rather common feature in supersymmetric theories. This V, or really V times some phase, is typically called a modulus. Okay, and corresponding to the, right, just as for in the Goldstone phenomenon, the fact that there are these degenerate vacua leaves you with a massless field. Okay, so now we've got a massless field, which is the relative phase of these 2 fields. Okay, so it's a real massless field. It's not the Higgs thing. Okay, so we've got that. We've got a massless field corresponding to the fact that it doesn't cost us any energy to change this V. So we have 2 massless bosons, or the right degrees of freedom of one complex field. And we have a linear combination of the fermions. So one combination, the psi plus plus psi minus psi minus rather, okay, paired up with the gaugino and gauge mass. The orthogonal combination is massless. So we actually have a massless fermion. And we can describe this modulus by field, okay, which I can write in the following way. I can write it as phi plus phi minus. So it's a nice gauge invariant object. Okay, and I can figure out what it is by perturbing around the minimum. So by writing phi plus let's call it V plus delta phi, and phi minus is V, delta phi plus, and V is plus delta phi minus. Okay, and then you can check that the linear combination, which is massless, is exactly the linear combination you guess from here and guess from the d squared term in the Lagrangian. Okay, so again, this is a rather generic phenomenon for people who are, for example, interested in string theory, in any string theory we understand, as opposed to the string theories which David doesn't want me to talk about, which we don't understand. In any string theory we understand, we have these kinds of moduli. We have these kinds of fields. And they're actually closely related to the sorts of things that Eric was talking about this morning also. Okay, these are the questions you should be asking him about in what sense, because these fields are like the couplings that he talked about. Okay, so this phenomenon is again rather generic. And also, because again, we can prove, I'll leave this again as an exercise for you, but you can even more easily than before prove a non-renormalization theorem that guarantees that in this theory, okay, this vacuum degeneracy persists to all orders. And this is not a feature of, generically, of non-supersymmetric theories. Okay? All right. So we now know a little bit about gauge theories. We know a little bit about chiral theories. Let me actually mention one more thing about gauge theory. So this was the abelian theory. Let me do a non-abelian theory. And just to illustrate this phenomenon again, yeah. Well, no, let me not do that. We'll come back to that. Since I'm instructed to end at really 1, 2, 3, 0. Okay, let me discuss something slightly different. Let me come back to this soft breaking of supersymmetry. Okay. So we talked about in this phi cube theory, we talked about this cancellation. okay, of the fermion loops and the boson loops. Okay, and we can now, right, so we saw that if we added a term, so we perturb the Lagrangian, so I'll call this delta all soft, was m soft squared minus m soft squared phi squared. We saw that the correction to the scalar mass was, so delta m phi squared was minus m soft squared. And we had, I'd say I had some lambda squared over 16 pi squared, right? And there was a log of a cutoff squared over this m soft squared. And this is sort of the thing we decided yesterday we were looking for. This is the analog of what we saw for the electron, and it's consistent with the 't Hooft. Right, who told us that that it's natural for a parameter to be small, in this case m soft, provided that in the limit m soft goes to 0, okay, the theory becomes supersymmetric. Right, it has a larger symmetry, a symmetry which guarantees the vanishing of this mass. Okay, so I want to generalize this to a theory with gauge fields and with gauge fields as well. And so more generally, the soft terms that we're allowed to write, the soft terms that are soft in the same sense, they're all terms with some dimension. Okay, they're all terms which break the supersymmetry. And so we're allowed to write mass terms for scalars. And we're actually allowed to write two types. We're allowed to write phi star phi and phi squared, or phi plus phi star squared. I should write plus. Okay, so we can write terms of this type. And we can write mass terms for gauginos. So we can write things like m lambda, 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 plus complex conjugate. Again, a mass term like this is a complex number. We're going to count parameters in a minute, so we want to remember that they're complex. Okay? And we can write cubic terms for scalars, cubic potential terms for scalars. A phi cubed. All right? So these types of terms, these are sort of the soft terms we can write. You could say, well, why didn't I write a mass term for the chiral fermions? And I could do that, but I can then do some bookkeeping and put that back in the superpotential and then fix these mass terms. So this is what I can write. Okay? And they all have this feature, this 't Hooftian type feature. Okay? So you can check. You can do little computations and check that, again, you get just these log divergences. But sort of it has to be kind of by dimensional analysis. Okay? So knowing this, let's think about the standard model and trying to supersymmetrize that. So we're going to write a supersymmetric version of the standard model. Okay, and so how would we go about that? So first of all, of course, and I'm out to describe the real world, or kind of describe the real world. So I'm going to want to I have to use this fact that I'm allowed to add these soft breakings, that a 't Hooft allows me these soft breakings, in order to get rid of the things that I haven't yet seen, half of them, more than half really. So let's see how that would work. So what we're going to do, we're going to first of all introduce a chiral field for every fermion of the standard model. So I have things like a quark doublet. I think I'm going over to the other blackboard. This one's going to drive me crazy. So let's do it here. Okay, so I can have a quark doublet. Okay, I can have a singlets. Okay, and there's some flavor index here. So 3 flavors, right? And I have lepton doublets and lepton singlets. Okay, I'm going to introduce vector fields for every. I'll call it VI or something. I don't want to call it I. Call it V, but a vector field for every gauge field of the standard model. So for the SU3 cross SU2 cross U1. Okay, and I'm going to introduce, and I need to introduce Higgs fields. Okay, and I could try and introduce one Higgs doublet. Okay, but that's going to be illegal for several reasons. Most prominently because we have anomalies. Okay, so if I introduce one Higgs doublet, because I have a fermion in the multiplet, okay, I'll have anomalies. Okay, so if I have, for example, what I'll call HU, which is a doublet, so it's an SU2 doublet with hypercharge +1, I also have to introduce an HD, which is a doublet with hypercharge -1. Okay, so I need these 2 Higgs doublets. Okay, and that's the field content of the theory. Okay, that's all I need as far as fields. I've more than doubled the fields of the standard model, but this is the field content of the theory. Okay, and then the Lagrangian. Okay, what's the Lagrangian going to look like? So first of all, I'm going to write the supersymmetric terms. So most of the supersymmetric terms are determined by the gauge symmetry. So all the kinetic stuff is determined by the gauge symmetry. I don't need to think about it very much. I do have to think about the superpotential. And so what am I allowed to write for the superpotential? The superpotential looks a lot like what I write for the usual Yukawa couplings. So I can write, for example, some matrix YU, Q U bar HU. The YU is a matrix in this flavor space, in this generation space. And then I have plus YD, Q D bar HD. Okay, so, and then I have YL, Q, I'm sorry, L, E bar, HD. Okay, so I'm allowed to write that. I'm allowed to write a mass term for the Higgs. So I can write mu HU HD. That's also gauge invariant. Okay, and then there's other stuff I can write. So this is my first problem. The next problem is like, so this stuff, just to remind you, this has hypercharge 1/3. This has hypercharge -4/3. This has hypercharge 1. You can check all the quantum numbers match. Everything is invariant. Okay, there are now some additional stuff I can write. So I can write, for example, I can write some coupling with U bar, D bar, D bar, with some flavor indices, F prime, F double prime, lambda, F prime, F double prime. Okay, this looks bad. Okay, right? This has quantum numbers of this has baryon number. I'll call it delta B equals -1, delta L equals 0. Okay, it doesn't carry any lepton number, but it carries baryon number. That sounds bad. Okay, yeah, I can write something. I'm not going to write so many indices. I can write something which looks like Q L D bar. Okay, L has the same quantum numbers as far as gauge quantum numbers, has the same quantum numbers as the HD. So every place I had HD, I could stick in L. Okay, I can write things also like HUL. Okay, so this was a term with delta B equals -1, delta L equals 0. This has delta L equals 1, delta B equals 0. Okay. Yeah. Not gauge symmetries. Well, I'm about to give a rule. I'm about to give a rule. And then later, because later I'm about to give a rule, and then later I want to get rid of it.
No, but I just say, so what's the logic? You could do it, of course. You could have done the standard model.
No, I can't. In the standard model, no, these are dimension 4 couplings. These are renormalizable. So in the standard model, I do it too, right? We all believe, I mean, you know, you are also probably in the same list, petition list. I want $1 billion to go and look for that extra order of magnitude in proton decay, right? So if we have grand unification, we generate those. We have, you know, those operators are surely there. Those operators are surely there somewhere. You know, and
but what's the point to write in supersymmetric standard model, you just said that
this is, I guess, the question period.
When it breaks, when it is broken, then there is higher perturbation corrections.
Yes, yes, but there I'm relying on a tuft, right? The goal, remember, was to resolve this question of naturalness, right? Why is it that the Higgs is light? We want to try and explain why the Higgs is light. And we can write all that, all this stuff is consistent with wanting the Higgs to be light. I should back up just to stress David's point. In the standard model, I could write an operator with 4 quarks, okay, or with 3 quarks and a lepton, okay, which would be a delta B equals 1, delta L equals 1 operator, okay, which violates baryon and lepton number and leads to things like proton goes to pi0 positron, for example, right? Okay, and people go down and deep in mines and look for that.
The point is that maybe the standard model have approximate supersymmetry.
Yeah, so if we look at lower energies, the standard model would, well, if we look below, yeah, so if this is right, then at some energy scale, you're going to see these other degrees of freedom. Below that energy scale, this is all, so we're going to imagine some, so I have 30 seconds left, so I want to take more questions. And I'm going to leave you, in fact, with some of you know the answers to all these. We're going to have to make some excuse for forgetting about these bad things. Okay? So in a sense, this is already bad, and you might have given up at supersymmetry at this moment. And people from the very beginning argued this was an issue. Okay? So you could say, you could add these terms, we need to forbid them. And we're going to forbid them, and I tell you the answer already. We're going to forbid them by a symmetry. Okay? But we're going to talk later about what we merely might want to do and whether we really want to forbid them or just suppress them, for example. Okay? But for the moment, but what we'll first do is we'll argue for a symmetry. The bonus of that symmetry will be that this symmetry is called R parity, and most of you are, I'm sure, familiar with it. That symmetry will leave us with a stable particle, which will be a dark matter candidate, and we'll do, following Slava's talk of yesterday, we'll be able to do the most simple-minded computation, which shows why it is truly is a plausible dark matter candidate, something you might have produced thermally in the early universe. Okay, and then we're going to talk about all these soft breakings in more detail. The first exercise we'll do is we'll just count them. Okay, and then we'll talk about Higgs physics, because Higgs physics right now is the thing that we should all be lying awake worrying about. Okay, so we'll talk about Higgs physics, and we will have heard this afternoon about exclusions of supersymmetry also. So we're going to have to think about how we combine, whether we can combine, and how we would combine those things, and whether this is a set of viable ideas. Okay.
You mentioned the tutorial?
And I mentioned the tutorial. I have been very dutiful here. Okay, so again, there's a tutorial, and as requested, I'll stop now. But as people are exiting, if there are more questions, but tomorrow we'll resume. We'll deal with this. We'll spend about half an hour talking about this model, and then we'll start turning to supersymmetry breaking and the dynamics associated with that. Okay. Okay.